In Chapter 3, Section 3, we make use of division, specifically long division and a synthetic division, which is probably going to be new, and use it to start putting together all the pieces we've learned to figure out how to factor and graph or solve these polynomial functions. Now you'll notice that your guided notes start with a warm-up after 3.2. This is an excellent review for the things that we went over in 3.2. We're not going to take the time to go through it right now. We're going to start on that second page where it's titled Way Back. So this is where we're going to start our 3.3 guided notes. Now, way back, because we probably have not done long division without your calculator for several years, until at least not unless you are forced to. We need to think about our vocabulary for division. When we're dividing, we take a dividend, divide it by the divisor, and the answer to our division problem is the quotient. That's what those terms look like in our long division symbol, that doghouse. The dividend is what the number that is being divided, the divisor is what we're dividing by, and the answer is the quotient. More frequently, we see our division problems presented in fraction or ratio form, where we have the dividend in the numerator, the divisor in the denominator, and again, the quotient is the answer to our division problem. So let's work a long division problem, standard arithmetic long division, and see what we get. See, just to remember what that process is. The process is repetitive, and the process that we're going to use with long division for polynomials is very similar. So I'm just going to give you a big long division problem. We're going to do 237,126 divided by 5. Now I picked my numbers on purpose as things that it's not going to go nicely. We have to do just a little bit of work. But think about the steps you go through. You ask yourself a question: how many times does 5 go into 2? And the answer is it doesn't. So we move over and we say, okay, how many times does 5 go into 23? Well, 5 goes into 23 4 times. And that number, that value, goes in my quotient line above the 3 because that's the last digit we used. After I put a value in my quotient line, I multiply. 4 times 5 is 20. And after I multiply, I subtract. So 23 minus 20 is 3. And then typically with long division, we just bring down that next digit. But because this is what I'm going to ask you to do in polynomial long division, we're going to go ahead and bring everything down for this example problem. And we start the process all over again. We ask ourselves, how many times does 5 go into 3? It doesn't. How many times does 5 go into 37? Well, 5 goes into 37 7 times. And then I multiply. 7 times 5 is 35. And then once again, I subtract. When I subtract, 7 minus 5 is 2. I bring everything else down because I'm going to keep going. And I ask the question again. You see that loop we're working through. We're doing the same steps every time. How many times does 5 go into 21 this time? Well, 5 times 4, and notice I'm keeping my columns lined up. This 4 goes over that 1, and we're keeping it lined up all the way down. 4 times 5 is 20. We already calculated that. After I multiply, I subtract. Bring down my remaining digits, keeping things lined up. Ask my question, how many times does 5 go into 12 this time? And that's 2. Then I multiply. 2 times 5, my quotient line times my divisor, gives me 10. And when I subtract this time, I get 26, and I've almost run out of room. And I get to go through one more time and say, okay, how many times does 5 go into 26? Well, it goes 5 times. 5 times 5 is 25, and when I subtract, I have 1. Now, I have different ways to deal with that 1. Hopefully you remember some of your options. You could just say remainder 1. That's what's left over. It doesn't go exactly, 5 does not go exactly into this value. There's 1 left over. I could add a decimal 0 and keep going. If I added a decimal 0, this would become 10, and 5 goes into 10 2 times. So my quotient would be 47,425 and 2/10, 0.2. The third way I can deal with this remainder is to bring it up and to write it as a fraction. My remainder is a positive 1 out of 5 pieces to make a whole. So my remainder goes on top of my divisor to create a fraction. This is the method that we're going to use to deal with remainders when we're doing polynomial long division. All right, so now that you remember how to do long division, let's do some long division with polynomials. We're going to use two types of division. Like I said, long division and synthetic division. Long division is going to look familiar. Synthetic division is going to look new. Synthetic division is a little quicker and a little more fun for most students than the long division. But there are times you have to use long division, so we're going to make sure that you practice. First, we have a theorem. The remainder theorem tells us that if r is the remainder when the polynomial function p of x is divided by an expression x minus c, then r is the value of the function at c. So the remainder, again, you don't have to memorize the theorem, just understand what it means. The remainder theorem tells us that when I do division, the remainder is the value of the function at c. So if I plugged in c, the function value that I get out, the result I get out, is going to be the remainder if I'm working division. Now, I deal with division differently depending on whether I'm using long division or synthetic division. If I'm doing long division, then my divisor is that expression x minus c. If I'm doing synthetic division, that we're going to learn here shortly, I don't use x minus c, I just use c, that value. Keep in mind that that means there's a sign change. Think about this. So with long division, if I were dividing by x minus 3, when I go to synthetic division, what is the value that I've plugged in? Well, I start with x minus c, just like x minus h. So what I'm using here is a positive 3. So for long division, if my divisor is x minus 3, if I choose to do synthetic division, the divisor would just be that value of c, or 3. Another example, if I'm doing long division and my divisor were x plus 5, what would I divide by with synthetic division? Well, this starts out as x minus, so I changed the sign. I would have plugged in a negative 5. Okay. Starting with long division, remember this key that with long division, we must have every term represented. Must have every term represented. So I'm going to use 0 placeholders if there's a missing term. I need to make an adjustment here because I have a typo. Hopefully I fixed that before you printed. 2x cubed minus 5x squared plus 4x minus 6. So I have a third degree polynomial. There are 1, 2, 3, 4 terms represented, and no terms are left out. If I look at my exponents, I count my way down. 3, 2, 1, and this would be x to the 0. So I don't need any 0 placeholders here because every term is represented. But if you look at the next problem down, I have 4x to the 4th, a 4th degree polynomial, but I'm missing a column, I'm missing a term, I'm missing my cubed term, and I'm missing my constant. So when I work this problem, I have to make sure to use 0 placeholders for those values. All right, let's do finding p of 3 if my function, my polynomial function p of x is this function. Again, we don't have to worry about any 0 placeholders because every term is represented. My dividend is the polynomial function. I'm going to make sure I give myself space to keep every column lined up. My divisor, okay, now we got to think about this. The value is 3, that is c. Because I'm doing long division, I'm using p of c. So I need to turn this into an expression. My expression is x minus c If c is 3, I'm dividing by x minus 3. So that is my divisor. If I were doing synthetic division, I would just divide by 3. Okay, ask your question. Looks a little different. How many times does x minus 3 go into doesn't quite work? So what I'm going to ask instead is, what times x, this first term in my divisor, what times x gives me 2x cubed? Because I want to make that match. Well, what times x gives me 2x cubed? I can do a little side work and divide if I wanted to. 2x cubed divided by x, that would give me 2x squared because one of those x's would cancel out. So 2x squared times x would give me 2x cubed. That's what's going to go in my quotient line. It needs to go in the squared column because it is a squared term. So in my quotient line, I write 2x squared. That lining things up. Then I multiply. When I multiply, I'm going to multiply by both of these terms in my divisor. So I multiply 2x squared times x and I get that 2x cubed. Those terms should always match. That was my goal. Then I multiply 2x squared times negative 3. That gives me negative 6x squared. That doesn't matter. What matters is that this first term matches exactly. Now think about your long division. After you multiply, you subtract. When I subtract, I have 2 terms to subtract. So I need to think about subtracting both of those. That means it changes the sign on both of those terms. So if I think about distributing this negative inside, this becomes a negative 2x cubed. This becomes a positive 6x squared. When I add those 2 terms together, I'm going to get, well, these first terms add to 0. That was my goal, to eliminate that first term. Every time that should happen. I have a negative 5x squared and a positive 6x squared, so that is a positive x squared. And I bring down my remaining terms. Then I'm going to go through the process again, asking the same question. What times x gives me x squared? Because I need this term to match. Well, x times x gives me x squared. So I put a plus x in my quotient line. Then I multiply. X times x, that's that x squared that we wanted to match. Then x times negative 3 is a negative 3x. After I multiply every single time, my next step is to subtract. I'm subtracting everything. So the signs change on both terms. I have additive inverses. They are going to add to 0 every time. I have a positive 4x and a positive 3x gives me a positive 7x, and then I bring down my last term, minus 6. Go back to the beginning with my question. What times x gives me 7x? Well, a positive 7. That goes in my quotient line, then I multiply. 7 times x is 7x. That matches like it's supposed to. 7 times negative 3 is negative 21. That doesn't match, but that's okay. That gives us our remainder. When I subtract both terms, distribute the negative, this becomes a negative 7x. Distribute the negative, this becomes a positive 21. So when I look at my remainder, well, these add to 0 just like always. I have a negative 6 and a positive 21, which gives me a positive 15. My remainder I'm going to deal with by creating that rational expression. I bring it up here, and since I'm adding terms, I say, okay, this is a positive remainder, so this is going to be plus 15 over my divisor. So 15 out of x minus 3. This is the quotient and remainder when I perform that long division. The information it gives me, based on my remainder theorem, this tells me that if I took this polynomial function p of x and I plug in 3, the result would be 15, that remainder. So the point 3, 15 is a point on my graph. Now that was a lot of work to get that 15, right? I may not just need that 15. I may need this quotient. Or, more importantly, I'm trying to figure out if my remainder is 0. Because if my remainder is 0, I found a point on the x-axis, which is one of my x-intercepts or roots of the function that I'm looking for. And in that case, I definitely have to have this quotient. So it's not just this remainder that's important. The quotient is also important to us. Let's take a look at the next problem. I want to find f of 4 for this given polynomial function f of x. And remember, we talked about the fact that we are missing some terms. So we have some 0 placeholders that we need to be concerned about. My dividend is 4x to the 4th. I'm missing my cubed term. So I plug in a 0x cubed. That's my 0 placeholder. It's not worth anything, but it saves this column for me. Like up here, I need to keep things organized by columns. I need to be able to do that even when I'm missing a term. So I use those 0 placeholders. Anything times 0 is 0, so it's not worth anything. It just saves my spot. Reminds me, gives me something to subtract from if I need it. My next term is a negative 4x squared. Then I have plus 6x, and I don't have a constant, so I'm going to use a 0 placeholder for my constant. My dividend, what I'm dividing by, well, I want to divide by the value 4, so I plug that into the expression x minus c. I'm dividing by x minus 4. Let's do our division. Asking our question, what times x gives me 4x to the 4th? Well, 4x cubed, so that goes in that cubed column. Look there, that's why we needed that placeholder. Then I multiply. 4x cubed times x is 4x to the 4th. Those match. 4x cubed times negative 4 is a negative 16x cubed. Then I subtract. When I subtract, I change the sign on everything. I'm subtracting it all out. So this becomes negative and those add to 0. That leaves, and then this becomes positive, and that adds to a positive 16x cubed. And then I bring down the remainder of my terms. So minus 4x squared plus 6x plus 0, keeping everything lined up as much as possible. All right, I go back to my question. What times x gives me 16x cubed? Well, 16, and it's a positive here, so it's going to be a positive here, 16x squared, and I'm keeping my squared column lined up. All right, I've put my value in my quotient line. Now I multiply by both of these terms in my divisor. 16x squared times x is 16x cubed. 16x squared times negative 4 is a negative 64x squared. When I subtract both of those terms, the sign changes on both of those terms. So that first term, they add to 0. The second term, this becomes a positive 64x squared, and a negative 4 added to that gives me a positive 60x squared. Bring down the rest, plus 6x plus 0. And I go back and ask my question again. Now notice that the problems I'm giving you are ending up with a positive value here, so I have all pluses in my quotient line. That's just coincidence. It's not always going to happen. Sometimes you'll get a negative here, and in that case you would have a negative term in your quotient line. All right, back to my question. What times x gives me 60x squared? Well, that would be 60x. Multiply. 60x times x is that 60x squared. 60x times a negative 4 is a negative 240x. And once I've multiplied, I always subtract everything out. So it changes the sign on those terms. This becomes negative. That means those are going to add to 0 just like always. This becomes positive. So I have a positive 6 and a positive 240 for a positive 246x. And I bring down that plus 0. Next step, last time through. What times x gives me 246x? Well, a positive 246. Multiply. I get that matching term. And then 246 times -4, you're going to need to plug that into your calculator. I have it written down. I get a net minus 984, not 86. Guys, I got in a hurry. Minus 984. All right, subtract one last time. It changes the signs. So my remainder ends up being a positive 984. I bring that value up and put it at the end of my quotient line. So I have plus 984 out of or divided by my divisor, x minus 4. This is the quotient when I work that division. Remember that what this means is that I have a point on my graph at the coordinates 4, 984. So I didn't find an x-intercept this time. This expression is not a factor because the function value is not 0. Still an important step to be able to do. Now, synthetic division can do these types of problems, and synthetic division is quick and generally easier. Synthetic division cannot divide by a squared term. When I learn synthetic division, I can divide by an x, but I cannot divide by an x squared, x cubed, anything like that. So it's important to be able to know long division. You're going to need to be able to give the pieces of long division on my math lab. So you can't just cheat and do the synthetic division to get your answer. Also, you can't use synthetic division for a problem like this, where my divisor is not just x, but it's an x squared. When I set up this problem, I want to check for placeholder zeros. So this is my dividend, and this is my divisor. When I set up my problem, I need to use placeholder zeros. I've got 4, 3, I've got a 4th degree polynomial, 3, I'm missing a squared term, and that's it. I'm just missing my squared term. So I say, all right, 2x to the 4th plus 3x cubed plus that placeholder 0 for my squared term minus 7x minus 10. All right, here we go. My divisor is given to me as x squared minus 2x. Now I want to point out something to you, that when I started with a 3rd degree polynomial, I divided out a single x. I went down a step from 3rd degree for my dividend to 2nd degree for my quotient. When I started with a 4th degree polynomial, I divided out a single power of x. I went down one step, one value for my degree. My dividend was x to the 4th. My quotient is x cubed. That links directly. I'm dividing out 1 degree when I divide by x. Now, for this problem, I'm dividing out 2 degrees. So in my quotient line, instead of starting over just at x cubed, where I would subtract out 1 degree, now I'm dividing out 2 degrees. So my first value in my quotient line is going to be x squared. All right. What times x squared gives me 2x to the 4th? Well, 2x squared. So I've moved over 2 columns this time to line things up. That's why I needed that placeholder 0. When I multiply, 2x squared times x squared is 2x to the 4th. 2x squared times a negative 2x is a negative 4x cubed. Make sure that you line things up in the appropriate columns. After I multiply, I subtract. My first terms add to 0, just like they were supposed to. When I distribute this negative, this becomes a positive 4x cubed. So I have 7x cubed. And I bring down everything else, plus 0x squared minus 7x minus 10. Now let's see what happens next. What times x squared gives me 7x cubed? Well, 7x, a positive 7x. When I multiply, I have 7x times x squared is 7x cubed. Those match. 7x times negative 2x is a negative 14x squared. Keeping my columns lined up according to degree. When I subtract, I distribute that negative inside. This adds to 0, and I'm left with a positive 14x squared. Bring down the remainder of my problem and go through the loop one more time. What times x squared gives me 14x squared? Well, just 14. When I multiply, I get that 14x squared, and then 14 times negative 2x is a negative 28x. I subtract. Those first terms are going to add to 0. This 28 becomes a positive 28x. I have a negative 7 and a positive 28, so that gives me a positive 21x, and then I bring down that negative 10. Now, when you look, you see that my degree of my divisor is greater than the degree over here that's left of the dividend. That means I'm done. So this is my remainder. Bring it up to the top and I say plus 21x minus 10 over divided by x squared minus 2x. The degree of my numerator is less than the degree of my denominator, and I am done. Now, I can't talk about that as being directly a point on my graph because I would still need a value of x to plug in. Okay, so that's our practice with long division. You've got 3 good examples now. We're going to do synthetic division. Synthetic division is an alternate method for dividing polynomials, and with synthetic division, only the coefficients are recorded, which is what makes it a little quicker and simpler to look at and to work with. Reminder that we are going to divide by that x value by c, not by the expression. You still have to have every term represented, so I'm still going to use placeholder zeros if I needed, even for the constant. The hang-up with synthetic division is that I can only divide out a single degree. I can only divide by x. I cannot divide by x squared. Can't do that. So this problem cannot be done with synthetic division. It has to be done with long division. So if you look at these problems, you'll notice that they look like the problem that we just worked through. Hopefully you will recognize those right down to the fact that I need to fix that exponent so that that is a 5x squared. We already did this problem on the last page using long division, so you know the answer. You know what it looks like. I'm using the same problems intentionally so you can validate the fact that you get the same result either way. Okay, I structure my synthetic division just a little differently than what you're going to see in my math lab videos. So if you do the Help Me Solve It on my math lab, their structure, their design for how you set up the problem looks a little different. Same steps, I promise. You can do it the way I do it, or you can do it the way they do it. Does not make any difference in getting the answer. So I'm going to take my long division doghouse, and I'm going to basically turn it upside down when I do synthetic division. That's why I draw mine like this, because I want it to remind you of the long division doghouse. Now, with synthetic division, our divisor is just that value c. So we're dividing by 3, not by x minus 3. And I'm just recording the coefficients. I have every term represented, so I don't need to worry about placeholder zeros. I'm going to write down 2, negative 5, 4, negative 6. Notice that I don't bother putting a plus for positive, but I do make sure I include a negative sign. Okay, we are going to do the same steps over and over again with synthetic division, just like we did those same steps over and over with long division. First step is always to bring down your first coefficient. Then I multiply on the outside. So I'm going to multiply my divisor times this value I just brought down. Multiply on the outside. 3 times 2 is 6. Then I add on the inside. So I'm going to add together -5 and 6, and I get a +1. Multiply on the outside. My divisor multiplied by this 1 gives me 3. Then I add on the inside. 4 and 3 is 7. Multiply on the outside. 3 times 7 is 21. Add on the inside. -6 and 21 is a +15. Now this last value is always my remainder, so I kind of divide it off. I separate it off. Now I have a quotient with remainder, and I need to interpret that. I have a quotient with remainder, and I need to interpret it by putting the variables back in. So I'm going to bring this over and interpret my quotient with remainder. My original problem is 3rd degree. Using synthetic division, I'm only reducing that by 1 degree. So if my original problem was 3rd degree, this quotient is 2nd degree. So this first coefficient has to be for the x squared term, and then I count my way down without skipping anything. So where my original problem started as 2x cubed, my quotient is going to start 2x squared because of this coefficient. Then my next term will be plus 1x. I don't write the 1 as the coefficient because it's understood. And then since this is x, that means my next term is the constant. And this last one is the remainder. It's a +15. It goes over the divisor. Well, I divided by 3. I need to turn that into the expression x minus 3. There's my quotient with remainder. And if you look back where we just did that on the last page, same quotient and remainder. Long division, synthetic division get us the same result, as long as I'm just dividing by a single degree. Can't divide using a squared term, cubed term, anything else with synthetic division. Let's do another. This is the other problem that we did on the last page. Note that we need placeholder zeros. I have to have every term, including the constant, represented. So when I set up my synthetic division, I'm dividing by the value. I need to include just the coefficients. Don't leave out your placeholder zeros. So my 4th degree is 4. My cubed term is missing. My squared term is a -4. My x term is 6, and my constant is missing. That constant is going to be over my remainder. I cannot leave it out. Let's do our synthetic division. Bring down the first value every time. Multiply on the outside. Add on the inside. Multiply on the outside. 4 times 16 this time. Add on the inside. Multiply on the outside. 4 times 60. Add on the inside. Multiply on the outside. Add on the inside. This is my quotient with remainder. I need to interpret that by putting the variables back in. My original function was 4th degree. I divided out a single degree, so my first term here is cubed. So I have 4x cubed plus 16x squared plus 60x plus the constant 246 plus that remainder 984 over, and then I need to think about what that divisor would be as an expression, x minus 4. So there is my quotient with remainder interpreted. This allows me, when I start finding remainders of 0, to factor polynomial functions that aren't factorable for me otherwise. Let's do the next one. Divide x cubed minus 7x minus 6 by x plus 2. Well, I'm dividing out a single degree, so I can use synthetic division. Let's set this up using synthetic division. That means that my dividend is going to need a placeholder 0 for my squared term. And my divisor needs to be turned into c. This is x minus c, which means c would be a negative 2. That's what I'm going to divide by. We're going to do a couple of things with this. So let's make sure we leave a little space. I'm dividing by negative 2. My coefficients are 1 and then 0 placeholder for my squared term, minus 7, minus 6. So I have 1, 0, negative 7, negative 6, and I remember that that last column is always for my remainder, so I'm going to go ahead and mark that. When I do synthetic division, bring down the first term every time, multiply on the outside, add on the inside, multiply on the outside. Notice I did get a negative down here for the first time. Told you that was just coincidence earlier. Negative 2 times negative 2 is a positive 4. When I add on the inside, I get a negative 3. Negative 2 times negative 3 is a positive 6. When I add on the inside, I get a remainder of 0. So, remainder of 0 means that I have found a factor. I found a factor because it results in a function value of 0, which means that I have an x-intercept. That negative 2, 0 is on the x-axis. So that is an x-intercept, a root or a 0 of my function. Let's finish dividing it. All right. Let's interpret our quotient. I started with a third degree, so this is squared. So we have this factor, x plus 2. We know it's a factor because I have a remainder of 0. And then I have the quotient, x squared, 1 degree less than my original polynomial, minus 2x minus 3. Well, since I know this is a factor because the remainder was 0, so it's going to show up on my x-axis when I graph it, this is quadratic. I can finish factoring this polynomial. I already have the factor x plus 2. This is going to factor out. My signs are going to be different. 3 is prime. My middle term is negative, so that needs to be a negative 3. So x minus 3 and x plus 1. When I set each of those factors equal to 0, so that I set equal to 0 and I get negative 2. This I set equal to 0 and I get negative 1. This one I set equal to 0 and I get a positive 3. These are my roots or zeros of my function. If I want to graph this, each of the exponents on these factors is just 1. So for all of these, I have multiplicity 1, which means the graph is going to cross at each of those functions. Let's set up a graph here. Right there. What else do I know? Well, I know that my leading term is x cubed of my original function. The leading term is x cubed. It's a third degree polynomial, odd degree, so my ends are going to go in opposite directions, one up, one down. It's a positive coefficient, so it needs to be an increasing function, so it starts low, finishes high. What else do I know? I know my y-intercept. If x is 0, my y-intercept is negative 6. So y-intercept is 0, negative 6. So I've got this y-intercept down here at negative 6. I have x-intercepts at negative 2, negative 1, and 3. So on my graph, I've got negative 2, negative 1, and positive 3. And I know that those are all values where the function is going to cross the graph. They're not going to slow down or anything, just go straight across like a linear function. I'm starting low, finishing high because of my end behavior. So if I sketch this graph, it's going to look something like, I've got to relative maximum there. I'm going to come down. I've got a relative minimum down here somewhere, and then I'm going to come back up and finish high. So I've got a relative maximum between these two x-intercepts, and I've got a relative minimum down here. I don't know the values of this peak and valley. I don't know exactly how high or how low the graph goes, but I am certain about these x-intercepts and this y-intercept and my end behavior. So I am certain about the general shape of this graph. We just factored a third-degree polynomial, something that we didn't know how to do before today. Okay. The factor theorem is an important theorem that we always kind of use that we haven't talked about, as well as the fundamental theorem of algebra. Factor theorem, the number c, that value, for example here my value c was -2 in this last problem. That number c is a zero of the polynomial function if and only if x minus c is a factor of the function. When I see mathematically that if and only if, it means it works both ways. So if x minus c is a factor, then c is a zero. If c is a zero, then x minus c is a factor. When I use this in conjunction with the remainder theorem, I get that if the remainder is 0, then c is a root of the function, and x minus c is a factor. That's what we just did here. We said, oh look, we've got a remainder of 0. That means this is a factor, x plus c is a factor. This point is a 0 of the function, and I can finish factoring and graph. So all of these theorems we're starting to put together into something that allows us to do more than we could before. Okay, this allows us, like I just said, to use synthetic division to completely factor and graph our polynomial functions. So we're starting to put everything together that we've learned up to this point. Here's another example. We just did one. Here's one more. Determine if x plus 4 is a factor of this polynomial function. Now, it doesn't ask us to go ahead and finish it in graph, but we're going to go ahead and finish it in graph if it is. All right, synthetic division, because it's quicker and easier and I can. X plus 4 is the divisor. If I were doing long division, I'm dividing using -4, the value c, if I'm using synthetic division. I'm missing a term, so I've got to have a 0 placeholder for my squared term. Remembering that that last column is going to give me my remainder. Bring down the first number in synthetic division, multiply on the outside, add on the inside, multiply on the outside, that gives me a positive 16, add on the inside. Make sure you're watching your signs, that's going to make a huge difference. Multiply on the outside gives me a -12 for a remainder of 0 when I add on the inside. So let's think about interpreting this. I found a remainder of 0, so that means that this is a root or a 0 of the function, and x plus 4 is a factor of the function because the remainder is 0. Since this is a factor, this comes down when I finish factoring it as x plus 4, and then I take my quotient and interpret it. My function started as third degree. I factored out a single degree, so this quotient is squared. X squared minus 4x plus 3. Now I know how to factor a quadratic, so I choose to just finish factoring. Signs are the same. They're both going to be negative, so I have x minus 3 and x minus 1. Which means when I set each of those equal to 0, I get the roots or the zeros of my function. I have x equals -4, x equals +3, and x equals +1. Again, when I look at these three factors, they all have an exponent of 1. So the multiplicity at each of these roots is 1, and the behavior is that the graph will cross at each of those roots. So let's set up our graph. We need to think about our leading term. Our leading term is x cubed. So our behavior again, just like the last example, because we have a positive coefficient and an odd exponent, our behavior is to start low, finish high, an overall positive increasing function. Y-intercept, if x was 0, so find p of 0, I get 0, 0, 12. So my y-intercept is at 0, 12. And we have some points we can put on our graph. So we're going to graph our y-intercept up here at positive 12. We have x-intercepts at negative 4, at positive 1, and at positive 3. And we know we're going to cross at each of those. Using my end behavior, I'm going to start low, finish high. I need to make sure I interact with all of those points. So if I start low, I think about, you know what, that's going to balance, so I'm probably going to go up higher than that. Cross, cross, cross. None of them have an exponent greater than 1, so I don't need to slow down at any of those crosses. Notice that I made my relative maximum kind of halfway between these two x-intercepts because that's usually where it happens. My y-intercept, don't make the judgment that that is always a maximum or minimum, relative maximum or minimum, because that's typically not the case. Okay, we're going to talk about what is going on with my end behavior. With my end behavior, I'm interested in what the graph is doing as x gets large, either in a positive or a negative direction. So as x approaches positive infinity, as x gets large in a positive direction, what's y doing? Well, y is increasing, so y is also approaching positive infinity. What about as x approaches negative infinity? Well, as x gets large in a negative direction, goes to negative infinity, I see that my y value is dropping. My y is approaching to negative infinity as well. This is a notation that you will be seeing in my math lab and that you will need to understand and use. Okay, our last couple of theorems for today. This unit has a ton of theorems. Fundamental theorem of algebra. If y equals p of x is a polynomial function of positive degree, it has at least one 0 in the set of complex numbers. That 0 might be real or imaginary. So if we have a polynomial function, we have at least one 0, but that 0 does not have to show up on the graph. It's basically what this is saying. Again, don't stress about memorizing the theorems. Just understand. Then my in-root theorem, I mentioned this the other day. If p of x equals 0 is a polynomial function with real or complex coefficients and positive degree n, then when multiplicity is considered, my polynomial function has n roots. So basically, the degree of the function matches the number of roots. Now, they won't all be unique necessarily, but they will all be there. For example, let's take the polynomial function f of x, and I'm just going to make it big. We're going to have x plus 4 to the 5th, x minus 1 cubed, and x plus 7 squared. What degree polynomial is that? Well, if I add up my exponents, that is a 10th degree polynomial. That degree tells us a couple of things. It tells us that we have a maximum number of 9 turns when we look at the graph. It can't turn more than 9 times. It can turn up to 9 times, but it doesn't have to. And then my in-root theorem tells me that I have a total of 10 roots. They don't all have to be unique. In fact, I only have 1, 2, 3 unique roots for this function. I only have 3 unique roots. I will have negative 4 multiplicity 5, positive 1 multiplicity 3, and negative 7 multiplicity 2. So a total of 10 roots. If I were to write this out, I would have to write x plus 4 times x plus 4 times x plus 4 5 times, and then x minus 1 times x minus 1 times x minus 1, and then x plus 7 times x plus 7. That's how I would write it all the way out with 10 factors giving me 10 roots, but they're not all unique. I only have 3 different unique roots. All right, let's put it together. One final problem. I know this video is longer than most of them, but it's a lot of combining of information. Now we have already put it together for the most part on the last couple of problems we did because I'm not very good about weighting. I like to share all the information I can with you guys. But let's do this last problem together. We're going to solve and graph the polynomial function f of x equals 2x cubed minus 5x squared plus x plus 2 given, I'm given some information, given that 2 is a root or 0 of the function. So I'm given a heads up. I have a starting place. This is the polynomial function that I'm being asked to graph. To graph that, I need to completely factor it. Let's think about some stuff we know. We know the leading term. My leading term is right here because it's already multiplied together. My leading term is 2x cubed, which means it is third degree. Because it's third degree, I have a maximum of 2 terms because it's one less than my degree. And I have a total of 3 roots, but they don't all have to be unique. They can be, they may be, but they don't have to be. My y-intercept, if x were 0, this term goes to 0, this term goes to 0, this term goes to 0, and I'm left with 2. So my y-intercept is at 0, 2. My end behavior depends on this leading term. Odd degree means the ends go in opposite directions. Positive coefficient means that I have an overall increasing function. So this is the same end behavior I've been working with all day today. That was just a coincidence, sorry. How many roots do we have to find using synthetic division? Well, we've got a third degree polynomial. If I find one root using synthetic division, then my quotient goes down to squared, and I can factor a squared function. We know how to factor quadratics. So I only have to find that first root using synthetic division, and then it's quadratic and I can factor it. That is true because I start with a third degree polynomial. If I started with a 5th degree polynomial, I can't factor reliably until I get it down to squared. So I would have to find 3 roots using synthetic division if it were a 5th degree polynomial. You see, that's just a separate example. Okay, but we're doing this one. It's cubed. We only need to find 1 root using synthetic division. So let's set up our synthetic division. My starting place, my key, is that 2 is a root. So I'm told that 2 is going to give me a remainder of 0. Let's use our synthetic division, our coefficients. All terms are represented, so we don't need any 0 placeholders. When we do our synthetic division, we always bring down that first number, multiply on the outside, and add on the inside. Make sure you watch your signs. And sure enough, we get a remainder of 0. So we know we did it correctly. Let's interpret this quotient. So this is a root, which means the factor would be x minus 2. Don't leave it out. And then I've got my quotient. My original was cubed. I went down 1 degree, so this quotient is squared. If I had to go again, if I needed to use synthetic division again, I would use this quotient. I wouldn't go back to the beginning. I would go down to my reduced quotient. But I don't have to because it's quadratic and I can factor it. When I factor this trinomial, I have a 2x squared, so my factors have to be 2x and x. My signs are going to be different, so I need to pay attention. I'm going to use 1 in both places because it's just 1 times 1 here. I need to end up with a -1 as my middle term. So when I multiply my outside product, I get 2x. My inside product is x. If I need a negative in the middle, then I need this 2x product to be negative. So this is a -1, this is a +1. If you're a little concerned about that, go ahead and FOIL this back together and check your work. Okay, so those are my 3 factors. I can take those and set them each equal to 0 and solve to get my roots. So I get x equals 2. I get x equals 1/2 here. That shouldn't be 11, that should be 1. Good grief. Excuse me. So if I set this equal to 0, I get a negative 1/2. And if I set this equal to 0, I get 1. So those are my 3 roots. The multiplicity for each of them is 1 because the exponent is 1 on each of them, which means that the graph is going to cross at each of those roots. So let's set this up so that I have my x-intercepts and I have my y-intercept. My y-intercept, remember, was 0, 2. And I know my end behavior. So I have a root at 2. I have a root at negative 1/2 and a root at positive 1. I have a y-intercept at 0, 2. So we're going to go start low according to our end behavior. Cross, cross, cross. I know I have a relative maximum here somewhere. I have a relative minimum here somewhere. Not sure about the values, but that's okay. I'm sorry, I didn't have that up where you could see it well. Let's talk about our end behavior. As x approaches positive infinity and as x approaches negative infinity, what is y doing? Well, as x goes to positive infinity, y is also going to positive infinity. And as x goes to negative infinity, y is also going to negative infinity.